Most people have an intuitive sense of probability. Unfortunately, this sense is not often based on a foundation of mathematical principles, so people are victims of scams, misleading statistics, and false advertising. In this lesson, we want you to build on your intuitive sense of probability and give it a mathematical foundation. So we're going to move right into example 1. Find the probability of each of the following events. Now, tossing a head on one toss of a fair coin. Well, our options are heads, then tails. So that's our sample space. So there is a 1 out of 2 shot to toss a head on a toss of a fair coin. Now, when you talk about tossing 2 heads in a row on a toss of a fair coin, that means there's a couple different options there. You can toss a head and a tail then a head, and a tail and a tail. So there are 4 options that we have. There's only one that we want, so this will be 1 out of 4. Now we talk about drawing a queen from a standard deck of 52 cards. Well, there are 4 queens in a deck of 52 cards, so that means it'll be 1 out of 13. There is a probability of drawing a queen from a standard deck of 52 cards. Now, how about rolling the sum of 4 on a single roll of 2 fair dice? Well, because there's 6 sides on a fair die, there are 36 different options to roll on a roll of 2 fair die. Now, the only way you're going to get 4, you're going to roll a 1 and a 3 on each die, a 3 and a 1 on each die, or a 2 and a 2. So 3 over 36, which is 1 over 12. Now, if we look at E, it says guessing all 6 numbers in a state lottery that requires you to pick 6 numbers between 1 and 46 inclusive. So what we're going to do here, 46, choose 6. So in your calculator, you're going to do 46, choose 6. So 9,366,819. That's how many different numbers there are, different tickets we'll have. So to win will be 1 out of 9,366,819. So do 1 divided by this answer, be about 0.00, let's see here. So there's your odds of winning the lottery. Notice that in each of these cases, we first counted the number of possible outcomes of the experiment in question. The set of all possible outcomes of an experiment is the sample space of the experiment. An event is a subset of this sample space. Each of our sample spaces consists of a finite number of equally likely outcomes, which enables us to find the probability of an event by counting. So if E is an event in a finite, non-empty space S of equally likely outcomes, then the probability of the event E is the probability of event equals the number of outcomes in E divided by the number of outcomes in S. Now, if we look at this here, the number of outcomes S in our sample space and tossing a head on one toss of a fair coin is 2. The outcome that we want is 1. That's why it's 1 out of 2. Tossing 2 heads in a row on 2 tosses of a fair coin, well, what we're going to have there's 4 possible outcomes. Only 1 is the desirable outcome. In C, there are 52 possible outcomes because there's 52 cards. Only 4 are the desirable events that we want. In D, there are 36 different types of rolls that each dice can do together. Only 3 of those are the desirable event. Now in E, there are 9,366,819 different lottery tickets that can be made. Only 1 of those is a desirable event. That's why it's 1 divided by 9,366,819. Now, the hypothesis of equally likely outcomes is critical here. Many people guessed wrongly on the probability example 1D because they figured that there are 11 possible outcomes for the sum on 2 fair dice, and that 4 is one of them. The reasoning is correct so far. The reason that 1 over 11 is not the probability of rolling a sum of 4 is that all those sums are not equally likely. On the other hand, we can assign probabilities to 11 outcomes in a smaller sample space in a way that is consistent with the number of ways each total can occur. The table below shows a probability distribution in which each outcome is assigned a unique probability by a population function. So there's only one way to get the number 2, so 1 out of 36. There's 2 ways to get 3, 3 ways to get 4, 4 ways to get 5, 5 ways to get 6, 6 ways to get the number 7 on 2 fair dice, 5 to get 8, 4 to get 9, 3 to get 10, 2 to get 11, and 1 to get 12. Now we see the outcomes are not equally likely, but we can find the probabilities of events by adding up the probabilities of the outcome of the event as in the following example. Now, a red die and a green die have been rolled. What is the probability of event? Well, what's the probability that the sum is prime? Well, our prime number, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, and 11 is a prime. So we're going to add all those numbers up. So the probability of the event is going to be 1 over 36 plus 2 over 36 plus 4 over 36 plus 6 over 36 plus 2 over 36. Adding all these up, 1 plus 2 is 3, 7, 13, 15 over 36 is our probability. We can simplify that, dividing both by 3, you get 5, 12. Now in part B, the probability that the sum is divisible by 3. Well, the probability it's divisible by 3, we'll add the 3, 6, 9, and 12. Those 4 numbers are all divisible by 3. So we'll take 2 over 36 plus 5 over 36 plus 4 over 36 plus 1 over 36. So the probability of my event, 12 over 36, which reduces to 1/3. So the probability that the sum is divisible by 3 is 1/3. Notice that this method would also have worked out just fine with our 36 outcome sample space, in which every outcome has a probability of 1 over 36. In general, it is easier to work with sample spaces of equally likely events because it is not necessary to write out the probability distribution. When outcomes do have unequal probabilities, we need to know what probabilities to assign the outcomes. Not every function that assigns numbers to outcomes qualifies as a probability function. Now, a probability function is a function p that assigns a real number to each outcome in a sample space S, subject to the following conditions. The probability for O has to be between 0 and 1. The sum of the probabilities of all outcomes in the sample space is 1, and the probability in the empty set is 0. Now, the probability of any event can then be defined in terms of the probability function. Let S be a finite, non-empty sample space in which every outcome has a possibility assigned to it by the probability function P. If E is any event in S, the probability of event E is the sum of all the probabilities of all the outcomes contained in E. Now again, E is the event that we want to see. Now if we look at example 3, is it possible to weight a standard 6-sided die in such a way that the probability of rolling each number is exactly 1 over n squared plus 1? Well, our possible outcomes are 1, 2, 3, 4, 5, and 6. And this is our n value. 1 over n squared plus 1. The probability of those if we put 1 in there, 1 divided by 2, and then 1 over 2 squared is 4. 2 squared plus 1 is 5, so this will be 1 over 5. And then we'll have 1 over 10, 1 over 17, 1 over 26, and then 1 over 37. If you add all these numbers up, you get about 0.924. About 0.924. In order to be a probability function, it needs to equal 1. So since this is not a probability, since it doesn't equal 1, the sum of those probabilities, this is not going to be a probability function.